The world has recognized that antibiotic resistance is a big problem. The development of these antibiotic conjugates is the ultimate in specificity. It, in theory, should decrease the rate of development of antibiotic resistance.
I'm Jane Grogan, and I'm a scientist. I've been at this for more than 20 years now, and I think perhaps the only thing better than doing science is talking about the science. Lucky for me, I work in a place where I am surrounded by some of the brightest minds in research. However, there's usually not much time to just sit and talk. And that's why I'm so thrilled to be hosting this podcast. I'm going to step away from my lab today and chat with a colleague about some of the cool stuff we're working on, especially as we try to link these discoveries to new medicines. So grab your favorite drink, get ready to unlock your science brain, and join us for Two Scientists Walk Into a Bar, a podcast for biotech geeks and the people who want to hang out with them. Today we're going to be talking about a subject near and dear to my heart, immunology. Specifically, how the immune system works, and new ways we're looking at fighting bacterial infections like the so-called superbugs. Okay, so how often do you think about your immune system?
When I get sick, I do.
Maybe when I'm sick, or not every day.
Yeah, probably after the fact. More so after you're sneezing and coughing and stuff. But not so much right now. I mean, you kind of take it for granted, right?
Doesn't seem like you pay attention to your immune system until it seems to go down and you're like, oh, I gotta play some catch up.
All the time. I mean, sometimes we work in close quarters, and if someone's sick, I don't want that passing on to me.
Whenever I'm on the bus or like working in a small office or something, and there's someone sick around me, I always think about it.
I think about it most when I'm sick and I really want my immune system to kick in so it gets rid of the sickness.
Not as often as I should.
Before we chat with our awesome guest, here's a brief primer on how the immune system fights off infection. We can divide the host response to possible infection into three phases. The first is the barrier phase. We've got skin, mucus, membranes, the things that act as a barrier to the outside world and to the world of bacteria and viruses. That's number one. Two is something we call innate immunity. That is the ability of the body to recognize something as foreign, something that's not supposed to be there, and eliminate it. And when all that fails, the third line kicks in. The third line of defense is what we call adaptive immunity. This is when our body illuminates infecting organisms that the innate system has failed to repel. Adaptive immunity distinguishes what's normally in our body from the invader and creates long-term memory. Got it? Okay, let's go. Chatting with me today is Rick Brown, one of the foremost infectious disease experts in the country. Rick was a professor both at Washington University in St. Louis and at UCSF in San Francisco, and he now heads up the Department of Immunology and Infectious Disease at Genentech. So welcome, Rick.
Thank you, Jane.
Why doesn't it work all the time? We have examples of chronic bacterial infections or bacterial infections that the immune system just cannot seem to get on top of.
A typical bacteria will divide every 20 minutes. Viruses can replicate many, many times in a minute. And so if you're a microorganism that's looking for a place to live, you have the ability to mutate, change in response to anything that our host can do so that you can find a niche to replicate. And so, in essence, that's why the immune system isn't perfect, because it can't respond in the same time frame as the bacteria can figure out new ways to challenge it.
So one of the ways we treat bacterial infections that we can't control ourselves is with antibiotics. How do antibiotics work?
Antibiotics work by interfering with a process that's necessary for bacteria to live. All the most successfully used antibiotics are based on big differences between bacterial physiology and our physiology.
The first antibiotic that was discovered was penicillin by Fleming back in the 1920s, right?
Right. So, yeah, Fleming discovered it by accident, and it wasn't really until it was possible to produce fairly large amounts of penicillin in laboratories or in manufacturing settings that it became useful for treating humans. It was in the early days very, very difficult to manufacture penicillin, and they used to collect people's urine in order to recrystallize penicillin out of the urine to give to the next patient. Actually, I'm not sure if it was the next patient or as the next dose to that patient.
Hang on, so they dose patients with the small amount they have.
Right.
That then collect whatever was...
And it's excreted in the urine, and it's a very small molecule, and many small molecules are excreted in the urine unchanged. And so they would collect urine and then re-isolate the penicillin from the patient's urine, and that would be the patient's next dose, so that they could essentially use the drug many times. We don't do that anymore. Now
we don't do that for anything anymore, really.
We don't do that. We don't do that at all anymore. But that's how it started. And penicillin was discovered as the product of a mold that came in through the window in Fleming's laboratory onto a bacterial plate. And he noticed that the bacteria weren't growing anywhere near where that mold was, and he reasoned that that was because the mold was making something that killed the bacteria. And so it was very smart observation of a complete accident.
I actually think that's a wonderful story of kind of accidental discovery rather than really hypothesis-driven research.
Because most of us would have looked at the plate and said, oh God, the experiment
What the
failed,
heck?
and
Throw
thrown
out
it
the
out
plate, right.
without thinking about it again.
Yeah.
And he looked at it and said, something important is going on here. And from that came the concept that microorganisms could make things which inhibited the growth of different microorganisms. And so that led to the idea that if you took samples where there were lots of different kinds of bacteria or fungi, you might be able to find other antibiotics.
Because, of course, just back to this niche idea, it's not just the bacteria trying to hide, say, from us, the host. They're also hiding from each other and other fungi in the microenvironments that they're living in. And this then brings us to the pivotal work of Salman Max Waxman,
Right.
who, obviously Nobel Prize winner, but he used to like to play with dirt. Perhaps you can enlighten us.
Well, he was the one who systematically set out to find substances made by one kind of organism that would kill other kinds of organisms. And he would just bring dirt from all over the place into the laboratory and grow whatever he could from that dirt, now doing on purpose the experiment that Fleming had done accidentally by taking different bacteria and putting them on plates of other bacteria and see who inhibited whose growth. And discovered many important drugs from that. But the most important antibiotic that actually doesn't interfere with human cells that Salman Waxman discovered was streptomycin. And streptomycin was the first drug that had any real activity against Mycobacterium tuberculosis, the cause of TB, tuberculosis. And tuberculosis was, in the late 19th and early 20th century, a huge problem for humanity. It is very easily transmissible from human to human, and there was no real treatment. It was a huge issue. So the idea that you could have an antibiotic that could kill TB was sort of the dream of every drug discoverer in the 40s and early 50s, and streptomycin was the first drug that could do that. And there are stories from that time of people who were essentially weeks from death, unable to get out of bed, who would be given a few doses of streptomycin and get up and dance. I mean, that's how quickly people responded.
Jane,
That is Wellington, my producer.
the story's over, right? We have the birth of antibiotics.
Not so fast, Wellington, because diseases fight back by changing. Perhaps you could comment a little bit about how we understand resistance.
Well, we can follow the story of streptomycin because these same people who were dancing ultimately died of TB. And the reason is that an antibiotic acts like any other big selective force. So it's acting on the bacteria and saying, if you are a bacteria which is resistant to this mechanism of killing, now you have the whole world opened up to you because all those other bacteria which were growing are now not being able to grow, and so you have a whole niche all to yourself. So even though they were literally 1 in a million when you started out, when you kill off all the others, they become the whole culture. And so now you're back to a TB infection, but in this case, The TB infection is all with bacteria that are resistant to streptomycin instead of sensitive to streptomycin. And in general, the same process happens with all bacteria when we treat people with antibiotics. That is, the bacteria which are resistant to the mechanism of action of the antibiotic suddenly have an open playing field in which to grow and proliferate and so forth. If the person who's infected transmits the bacteria to another person by any of the standard means by which we transmit infections,
Touching, coughing, whatever.
yeah, all that stuff. Then the new person getting newly infected now is infected with an organism which is already resistant to the antibiotic that was being used.
So where are we today?
So I would say there's 2 or 3 different strategies. For example, for penicillin, one of the common ways of developing bacteria responding to getting resistant to that is to make an enzyme which destroys the penicillin. So you could make a drug which worked like penicillin, but was resistant to those mechanisms of destruction. Another way of making new antibiotics is to say, well, let's go for antibiotics whose target is still something that's essential to bacteria, but not essential to us, so they could be safe, but is very different than any other antibiotics that have been used so far. And that's a potential way to go. It's more difficult, because these ways of trying to find antibiotics, like we just talked about with Salman Waxman and going through lots of dirt, have been tried over and over again through the years. And there's probably a diminishing number of those kinds of antibiotics. And then the third thing that we can do is to make antibiotics for which it's much less easy to transmit resistance from one bacteria to another bacteria, or which are so specific in their activity. That is, they work against Staph aureus, but not against Staph epidermidis and not against Streptococcus pneumoniae and so forth, that even if resistance develops, it won't affect so many bacteria as what happens now. Because what happens now is the antibiotics are so general in their activity that when a resistance mechanism develops, it develops in lots and lots of kinds of bacteria.
You know, one thing that you and your group is working on at the moment, which is very exciting, is this idea of antibiotic drug conjugates, and perhaps taking an antibiotic that may already be known, aside from these ones that may be discovered at the bottom of an ocean somewhere, and linking them up to an antibody that can be targeted really specifically to a bacteria. Perhaps you could, share some of the highlights of the work that you are doing.
The development of these antibody-antibiotic conjugates, of course, is the ultimate in specificity, because what you get is the specificity of the antibody, which recognizes only one kind of bacteria, and the activity of the antibiotic. So that was developed in order to be very specific and to not expose bacteria which are not doing you any harm at the moment to the antibiotics so that they can develop resistance to it. So in that way, it's a little bit of an answer to the antibiotic resistance. It, in theory, should decrease the rate of development of antibiotic resistance. On the other hand, that approach creates some problems of its own. The 2 main technical problems are because usually when we give an antibiotic, we just give it unconjugated to anything. We can make the concentration of that antibiotic be whatever we want. Whereas in the antibody-antibiotic conjugate, since the antibody recognizes the bacteria, the concentration of the antibiotic is limited by how much antibody we can get on the bacteria. And so we have to have antibiotics that are very, very potent.
Jane, how does this work exactly?
So instead of taking a pill where antibiotics just circulate around the entire body looking for something to attack, the theory is that we can target the invaders using antibodies which by nature only attach to certain or specific things, in this case the bacteria. And only when coming in contact with the intended target do they then deliver their payload. The design, similar to many of the new biologic cancer drugs, means that ideally it's toxic just to the invaders, but not to our normal cells. But it's kind of difficult in practice.
Finding those drugs is one thing, because not every antibiotic is suitable for use in that kind of a combination. And then the other problem that you encounter in making these antibody-antibiotic conjugates is that usually the antibiotic is not active at all when it's attached to the antibody. And so you have to bring the antibiotic to the bacteria with the antibody, and then at that moment, release it from the antibody so that it can work against the bacteria. And that's a trick that requires a lot of specialized chemistry to be able to do. And so we know two different ways to do that for the bacteria. One way is to use another activity of the antibody, which is that it induces host cells to take up the bacteria. So when we have the bacteria with the antibiotic conjugate on it that gets taken up by the host cell, then we use host cell enzymes that are present in that phagosome to release the antibiotic. So it's sort of using the host cell in a new way to kill the bacteria, a job which it was intended to do in the first place.
It sounds like a very exciting synergy of different mechanisms.
And the second way that we know to do that is to actually use bacteria-produced enzymes to release the antibiotic. And so sometimes we've made antibiotic conjugates in which we make the connection between the antibody and the antibiotic susceptible to an enzyme that the bacteria has made, probably to create this niche to cause a little damage to host tissues so it can sit there. And so that's, I think, an even cooler one, because we're using a bacterial factor which often causes disease to create the condition which will kill the bacteria.
So it could be a perfect scenario for an optimal drug. But I want to move into beyond just the treatment and these new ideas for treatments to diagnosis. When a patient presents, say in a hospital setting or at the clinic, before they get a diagnosis, they're often treated with antibiotics that may not be specific for what they actually have, but because we don't know what they have, they go on these broad treatments. And I just wanted to hear your thoughts on where you think diagnosis for bacterial infections is today and what the future looks like.
So in a standard clinic or hospital setting, diagnosis of bacterial infection today is no different than it was 100 and some odd years ago.
It's unfathomable.
It's really pretty amazing that things have changed so little. And it requires getting a sample from the patient of the fluid that you think is infected and putting it on a bacterial plate or putting it under the microscope or something like that to get an idea of what the infection is. And of course, there are many, many technologies which could improve upon this vastly, but they've not come into broad clinical use precisely for the reason that you say, which is that the standard practice now in medicine, if somebody has a serious bacterial infection, to treat very broadly until you know exactly what the infecting organism is. But eventually, you start to build up toxicities as well, because none of these antibiotics are totally without toxicities. And as you add more and more antibiotics, you increase toxicities. You increase drug-drug interactions with whatever other drugs the patient has. It becomes an incredibly difficult situation. And so I think the period of time when this paradigm for treating serious bacterial infections, treating broadly initially, it's just not going to be possible.
So if we can use molecular screening techniques to really bring this down from days, which we do now with these cultures, to hours, then the hope is that we can really identify the exact infection and start providing really exquisite, specific treatments with things like these antibody drug conjugates or other.
Right. And so identifying the exact infection and also identifying the antibiotic resistance mechanisms which are present in those bacteria so that we know which drugs won't be effective against those bacteria, and so that the treatment can be tailored at a very early time to exactly the infection that patient has. And it seems to me that we are at a time in science where that is possible. If we can diagnose exactly what the infection is, we should be able to use narrower spectrum antibiotics, which will have less of a resistance problem.
So it sounds like there's a lot of positive potentials and therapeutic outcomes there for patients.
You know, I think as the world has recognized that antibiotic resistance is a big problem, and this problem is being attacked from many different perspectives. I've sort of given you the scientific perspective, which is, I think, the one that holds probably the greatest hope. but there are also perspectives related to hospital epidemiology and simple things like hand washing and so forth that will also have marked impact on the rate of antibiotic resistance and the transmission of antibiotic-resistant organisms and so forth. If we go back a generation or two in medicine, when I was a young infectious disease physician starting out, the chairman of medicine at UCSF said, we're not going to hire any more infectious disease doctors because infectious diseases are a thing of the past. And that was not an uncommon sentiment. A guy who was an infectious disease physician himself, who was the head of the American College of Physicians or some august group like that, also said, you know, if we train any more ID physicians, they'll be diagnosing each other's throat cultures or so, you know, I mean. And,
So cure was when
they
we were
had
done.
this vision of cure, and it was the hubris of not understanding the basics of how rapidly bacteria can develop resistance that led to that hubris. And I think that we're now quite aware of all these problems, and I think that there's a much greater understanding of how we're going to have to deal with this in the future.
Well, it sounds like there's great hope for patients, and in the meantime, we should keep our wounds cleaned, wash our hands, and try not to cough on each other too much. With that, thanks, Rick. It's been great chatting with you.
So thanks, Sam.
Amazing. For some time, the search for new antibiotics was something of a scientific backwater. Now it's one of the hottest fields in discovery research. I hope you enjoyed that chat as much as I did. And if you did, please tell your fellow science fans about the show. We'll be back in a couple of weeks with a new podcast. If you haven't listened to our previous episodes, now's your chance to catch up. And while you're at it, we'd sure appreciate it if you'd follow us and like us on Facebook and Twitter. And importantly, rank us on iTunes. That's our ultimate data point. I'll talk to you again soon. But for now, I'm going to wash my hands, and then for me, it's back to the lab.